AP Chemistry, Chapter 6, Lesson Video, Part 3. And in this part, we are going to cover Section 6.6 all the way through the end, which is Section 6.9. Now, these sections I'm going to go a little quicker through because it's not all that background information that connects to physics. It's going to electron configuration, and most of y'all seem to be really good at that. So hopefully you still are. If you do need a refresher, though, you need to go back to my honors chemistry lesson videos for Chapter 5. That's where I cover electron configuration in a little bit more detail. All right, so representations of orbitals. The s orbitals have a spherical symmetry, so they are shaped like a sphere. As n increases, the distance from the nucleus increases for s orbitals. Okay, so like 1s might be this big, whereas 2s is going to be larger, 3s is going to be even larger. Now remember, it doesn't make them be able to hold any more electrons, it just means they are farther from the nucleus. An intermediate point at which a probability function goes to 0 is called a node. So we're going to discuss how there are places where the electrons can't be, and those are in between the energy levels. And so we refer to that as a node. So as you kind of put the 1s, 2s, and 3s and you overlap them, you'll notice that 3s is not completely solid on the inside. Okay, we have those nodes where the electrons are not allowed to be. So p orbitals, the electron density for p orbitals occurs in two regions on either side of the nucleus, separated by a node. The two regions are called lobes. So remember, p has 3 orbitals. They look like this, so notice it has the two kind of balloon or teardrop shapes on either side. There's a node in the middle, all right? But they all three overlap. So when they overlap, it looks like this. Each p orbital has the same energy. So as long as they're all 2p, they'll have the same energy. Now 3p would have a different energy than 2p, but all the 2p orbitals will have the same energy. So there are 5 d orbitals, which all have the same energy. They look like this. Remember we talked about it either looks like a 4-leaf clover or 2 lobes with a donut around the middle. And then of course F has 7, which all have the same energy. And then of course G has 8, which have all the same energy, but of course we don't have enough to fill in G. All right, so section 6.7, many electron atoms. In many electron atoms, the electron-electron repulsions cause the different subshells to have different energies. So for example, in hydrogen, 2s and 2p have the same energy because they're both the second energy level. But that's because hydrogen only has 1 electron. Hydrogen is the only atom that only has 1 electron. So every other atom is a multi or mini electron atom. And so once you have more than 1 electron, the electrons repel one another, and that puts 2s and 2p at different energies. They're still close to each other, but they're not identical as they would be in hydrogen. So orbitals with the same energy are degenerate. Okay, so 2s and 2p are not degenerate, but the 3 2p orbitals are degenerate because they're all together. They're all the same energy. So this is the order of the sublevels, but of course if you remember in honors, we don't use this, we follow the order on the periodic table. So electron spin is a property that causes electrons to behave as if it were a tiny sphere spinning on its own axis. A spinning charge produces a magnetic field. Well, since everything or all matter is made of atoms and all atoms have electrons, you may think, oh, well that means everything is magnetic. Well, the two opposite directions of the spin therefore produce tiny oppositely charged magnetic fields. So that's why we talk about the electrons spinning clockwise versus counterclockwise. So if they're spinning in opposite directions, those magnetic fields end up canceling out. So that's why everything in the world is not magnetic. The Pauli exclusion principle states that no 2 electrons in an atom can have the same set of 4 quantum numbers. So each orbital can hold a maximum of 2 electrons and they must have opposite spins. Okay, so Pauli exclusion principle states an orbital can hold at most 2 electrons, and if 2 go in the same orbital, they must have opposite spin. Okay, we've already discussed that before. So, moving on real fast to section 6.8, electron configuration. The way in which the electrons are distributed among the various orbitals of an atom is called the electron configuration. And so remember, we don't draw a picture because you saw those orbitals. Those pictures would get very complex. We list it. Aufbau's principle states that electrons fill the orbitals in order of increasing energy. So that's why we always start at 1s, and then we move on to 2s, and then 2p. We go from low to high energy. Electrons having opposite spins are said to be paired when they are in the same orbital. An unpaired electron is one that is not accompanied by a partner of opposite spin. So for example, if the question asked how many paired electrons do I have? Well, these two are paired, these two are paired, these two are paired. So we have 6 that are paired. So see how there's one up and one down in each orbital? But if it said how many unpaired, those are ones that don't have a partner. So it would be 2 unpaired electrons. So when you're asked about paired versus unpaired electrons, drawing the arrow configuration is more helpful than doing standard. Because standard, you wouldn't actually see the orbitals, you'll just see the power. You would just see D with the power of 2, 4, 8. So you would have no idea. So whenever you're asked about paired and unpaired, always do arrow configuration. So Hund's rule states that for degenerate orbitals, the lowest energy is attained when the number of electrons with the same spin is maximized. Hund's rule is based on the fact that electrons repel one another. Okay, so remember, we've discussed this rule before. If I have 3 orbitals for P and I only need to put 2 electrons in there, they would rather be separate than paired. Okay, so we want to fill it in like I did in class. Just go up, up, up. Then if you still need more, go back and put your down arrows. Alright, so sample exercise 6.7. It says draw the orbital diagram for the electron configuration of oxygen. How many unpaired electrons does an oxygen atom possess? Alright, so for this, whenever it says orbital diagram, that's another way of saying arrow configuration. Because some of them will call it that instead. That just means you're not doing standard. Okay, so I need to do arrow configuration. So I find oxygen on the periodic table. So remember, y'all, we're going to start at hydrogen. So at hydrogen, we're at 1s, 1 orbital, 2 electrons. 1 for hydrogen, 1 for helium. Now I'm at lithium. So I'm at 2s, 1 orbital, 2 electrons. Lithium, beryllium. Then I move on to boron. I'm at 2p, 3 orbitals. So it can hold up to 6 electrons, but I'm going to stop at oxygen. So I have boron, carbon, nitrogen, oxygen. So I need 4 electrons. So remember, I don't want to do up, down, and leave this one blank. I want to go up, 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 and then I need 1 more that's down. Okay, so that's my orbital diagram or arrow configuration for oxygen. Then it says how many unpaired electrons does an oxygen atom possess? Well, these are my 2 unpaired electrons, so there's 2 unpaired electrons. So see, if you wrote it in standard, then it's harder to decide how many electrons are unpaired or paired. Okay, so that's why using arrow configuration, or like I said, some people call it orbital diagram, that makes it easier to see which ones are paired and which ones are unpaired.
Good afternoon, teachers and students. Please pardon this interruption.
So,
Jaden White,
try this
please
one.
come to the
I'll
front
assume
office.
you've done that, and then we'll look at it
Jaden
together.
White, you're needed in the front office.
So it says
Thank you.
So it says write the electron configuration for phosphorus. How many unpaired electrons does a phosphorus atom possess? All right, so I'll assume you've tried that, so let's look at it together. So we're going to phosphorus this time. Okay, so I'm going to start at hydrogen, so I'm at 1s. This one, it doesn't actually specify which type, but because it's asking about those unpaired, I'm going to go ahead and do arrow configuration. All right, so I have 1s, I do 1 up and 1 down, hydrogen, helium. At lithium, I'm at 2s, lithium, beryllium. I got 2p, so I'm going to do all 6. That gets me all the way from boron to neon. You may need a periodic table out if you haven't noticed already. All right, sodium, we're at 3s. I do 1, 2, sodium and magnesium. All right, and then I'm at 3p. I'm at aluminum. We're stopping at phosphorus. Okay, so I do 1 for aluminum, 1 for silicon, 1 for phosphorus. So I want those to be all split up, 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 up. All right, so there's my electron configuration, and then it says how many unpaired electrons. Well, here's all my unpaired ones. I have 3 unpaired electrons. And that's all you have to do for that. Okay, 3 unpaired electrons. So y'all should be really good at these, because electron configuration is usually a lot of people's strong point. All right. So noble gas configuration, we already learned about that. That was y'all's favorite because it's the shortest. In writing the condensed or noble gas electron configurations, so see, notice sometimes they'll be called condensed, the nearest noble gas of lower atomic number is represented by a symbol in brackets. The inner shell electrons or core electrons are left out because they are all taken care of when you put that noble gas in brackets. Only the outer shell electrons or valence electrons are used. Okay, so for example, if I wanted to do vanadium, I would start with argon in brackets, and then I would just fill in that last unfilled sublevel for vanadium. Oh, okay, I guess no examples because I just already know you know how to do this. All right, so moving on to section 6.9. So see, this is what I mean, y'all. If you're struggling with electron configuration, go back to my Honors Chemistry Chapter 5. It's section 5.2 lesson videos. That's where I extensively cover electron configuration, all three types, aero, standard, and noble gas. All right, so electron configuration and the periodic table. The periodic table is structured so that the elements with the same valence electrons are arranged in columns. Okay, so as we already know, these are where our S sublevels are. Our P is over here, our D is in the middle, and F is at the bottom. If you ever forget where one of them is, you can just count the elements. So like say I wasn't sure if this was P or D, I can say, okay, 1, 2, 3, 4, 5, 6, which sublevel holds 6 electrons? P. And so of course D, if you count across, it's 10, and F, if you count across, it's 14. So that's an easy way to keep them straight. So it says, what is the characteristic valence electron configuration of the halogens? Okay, so y'all, our halogens are group 17. That's first and foremost important. You got to know where the halogens are. Okay, so the halogens are group 17. So for group 17, notice it said the characteristic valence electron configuration. Valence electrons are the highest S and P sublevel. Okay? So it's your highest S and P sublevel. So for our halogens, it's in group 17. So we should have gone through S. Like, let's just pick one, just so I can show you an example. Let's just pick fluorine. Okay, fluorine, I have 1s2 for hydrogen and helium, 2s2 for lithium and beryllium, 2p5. That would get me to fluorine. Okay, so it's the highest S and P. So if you look, my highest is 2s2, 2p5. But it asked me about any of the halogens. So that's where we replace the number with an N, because it could be any energy level. It could be 3s2, 3p5. It could be 4s2, 4p5. So we just write ns2, np5. And so I can see that all the halogens should end in a number s2 and that same number p5 because of where they're located on the periodic table. And y'all, the more you can understand electron configuration just by looking at the periodic table, the easier your life will be. Okay, so they all end in S2, P5. And like I said, sometimes you'll see N's put in front of those to show that it could be any principal energy level number. Remember, the N is just the principal energy level. So y'all try this one. Pause it, try it, we'll look at it together. So I'll assume you've done that. So it says, which group of elements is characterized by an NS2, NP2 electron configuration? Okay, so don't let the N's throw you off. That just means any S or P. So it could be 2S2, 2P2, 3S2, 3P2. All right, so S2 gets me across group 1 and 2, and then P2 gets me across group 13, and I end on group 14. Okay, so for this one, it would be group 14. Good job. All you have to do is look across the periodic table. Like, here's our periodic table. I'll just draw a quick one real fast. Okay, so here, these all end in S1. Here, these all end in S2. For P, we have P1, P2, P3, P4, P5, and P6. Okay, so see, this is group 1, 2, group 13, and 14. So once I got to P2, I was at group 14. That's all you have to do. So if they had said which one was NS2, NP5, or we already did 5, NP6, I would have said, oh, okay, it's group 18, or the noble gases. What if it just said NS1? Then I'd say, oh, it's group 1, or the alkali metals, like that. Okay, that's all you have to do for those. So don't overanalyze them. These are meant to be easy. All right, so it says, write the condensed or noble gas electron configuration for bismuth. how many unpaired electrons does an atom of bismuth possess? All right, so we're writing the noble gas configuration for bismuth. So first we find bismuth. All right, it's number 83. So the noble gas before it is Xe. All right, so then I'm just going to work my way across. So I'm starting at CS, number 55. So get a periodic table out, look at it, because we're going to have to make a little detour down in those F sublevels. All right, so I'm starting at CS, so I'm at 6S2, because that gets me through CS and BA. So now I'm going to hit LA, so I am at 5D, but I'm just going to put 1 for right now, because we're going to do LA, number 57, but then we're going to detour down to 58 through 71. All right, so I follow 58, so now I'm at CE, so that's 4F. I'm going to fill in the whole thing, so it's 14. So I go CE all the way through LU, number 71. Now I got to pop back up to number 72. 72 through 80 finishes off 5D. So I can go ahead and change that to 10. Now I'm at TL, so I am at 6P, but I'm not going to fill in the whole thing. I'm going to stop at bismuth, Bi, and so that has 3. All right, now, remember, we like to rearrange them. I will go ahead and let you know on the AP exam, I noticed that lots of times they will not rearrange. But remember, when you're trying to make a positive ion, you have to remember to remove from the highest energy level first. If you don't rearrange, you're likely to do that wrong. So I want you to rearrange in my class, but just know on the AP exam, a lot of times they don't rearrange. All right, so then it says, how many unpaired electrons? Well, we didn't do arrow configuration, but it doesn't matter. I can see S is full, D is full, F is, those are all full, so they're obviously all paired. So I can just do 6P real quick if I wasn't sure. It has 3, 1, 2, 3, so there's 3 unpaired electrons. So don't sit there and try to do arrow configuration for the whole thing. It asked me for noble gas. I don't want to waste my time doing the whole thing. So if you need to figure out unpaired, just go to that last unfilled sublevel, and that will show you how many unpaired you have. All right, perfect. So I'll let you try these. So you're just writing the noble gas configuration for the following. Okay, so pause the video, try it. It doesn't even ask you about paired and unpaired, so I'll assume you've done that. We'll look at them together. All right, so we have cobalt. So I find cobalt. The noble gas before it is argon. All right, so I go past argon to number 19. I'm at potassium, and I'm going to work my way across to cobalt. So I'm at potassium, so that's 4S2 for potassium and calcium. Now I'm at scandium, SC, and I need to go to cobalt. So I'm at 3D. I'm not going to fill in all of them. All right, whoops, and I just wrote a 10 after I said I'm not going to fill in all of them. All right, so I have SC, TI, V, CR, MN, FE, CO. So I'm going to put in 7. And then like I said, I know the AP exam will recognize this is the correct answer, but I want you to rearrange it, because if this had a charge, we would remove from 4S before we would remove from 3D. And I don't want you to miss that. So just go ahead and rearrange. All right, so hopefully you got that one right. Next we have tellurium, TE. So we find tellurium, number 52. So the noble gas before it is Kr. All right, so Kr is number 36. So that means I need to start number 37 and work my way across to tellurium. All right, so I'm at 37. So I'm at Rb, so I'm at 5s2. So that gets me Rb and Sr. Now I'm at Y. Y all the way through CD is going to be 4d10. All right, now I'm at In. I'm at 5p. So I say In, Sn, Sb, Te. 5p4. Okay, and so again, I'm going to go back and rearrange, because another thing, y'all, is they may say, like, how many valence electrons does this have? Well, then y'all are likely to just look at that and say 4. But remember, valence electrons are the highest S and P. So in this case, it's 6 valence electrons. And see, if you don't rearrange, you're more likely to miss it. So I feel like the rearranging is very important. But you know, that's just me. All right, so hopefully you got those right. So let's keep on going. All right, so odd electron configurations. sublevels are most stable when exactly half full or all the way full. Okay, so they're the best when they're all the way full, but they're still really stable if they're half full because at least it's all kind of symmetrical. It is more acceptable for a large sublevel to be stable. So if you're picking between S and D, D is larger, so it's more important for it to be stable. Most odd electron configurations, such as chromium and copper, are based on this fact. So if you remember, back in honors, we would take 1 from 4s and give it to 3d in chromium and copper in order to make 3d more stable. All right, so let's move on to this integrative exercise. So again, if you're struggling with chromium and copper being those odd electron configurations, go back to my chapter 5 lesson videos, section 5.2. All right, so let's knock out this sample integrative exercise and we'll be done with chapter 6. So it says boron occurs naturally as 2 isotopes, boron 10 and boron 11, with natural abundances of 19.9% and 80.1%. In what ways do the 2 isotopes differ from one another? Does the electron configuration of boron 10 differ from that of boron 11? All right, so first it says, in what way do the 2 isotopes differ from one another? Well, isotopes are different in their masses. So their masses are different. Obviously, boron 10 has a mass of 10, boron 11 has a mass of 11, and their number of neutrons are different. We'll just put div. All right, so boron's atomic number is 5. So that means boron 10 has 5 neutrons, boron 11 has 6 neutrons. Okay, so that is the way they are different from one another. But then it says, does the electron configuration of boron 10 differ from that of boron 11? Well, electron configuration is clearly based on electrons. Boron 10 and boron 11 still both have 5 electrons. So the electron configurations are the same. Electron configuration is not based on protons or neutrons, it's only based on electrons. Okay, so since the only difference is the neutrons, their electron configurations would be identical. All right, so that's what I said here. Isotopes differ from, oh, that should say from one another in the number of neutrons and the mass number. Boron 10 has 5 neutrons, boron 11 has 6 neutrons. The electron configurations for the isotopes would be identical because they are both atoms of boron that contain 5 electrons. All right, so it says draw the orbital diagram for an atom of boron 11. Which electrons are the valence electrons? Okay, so remember, orbital diagram is arrow configuration. All right, so we have boron. So I go 1s, hydrogen, helium, 2s, lithium, beryllium, 2p, I just need 1 for boron. All right, it says which electrons are valence. Remember, valence are the top S and P. So these right here are my valence electrons, which makes sense because boron is in group 13, so we know it has 3 valence electrons. So it would be those 3. All right, so hopefully it's all making sense. All right, so then it says indicate 3 major ways in which 1s electrons in boron differ from 2s electrons. All right, so we're listing 3 ways. All right, well, the 1s ones would be closer to the nucleus. 1s electrons are closer to the nucleus. Another is we could say 1s electrons have less energy because they're closer to the nucleus. And then another thing we say is 2s electrons are valence electrons. And 1s electrons are core electrons. Okay, those are 3 different things about the 1s and 2s electrons. All right, so here I wrote 1s are at lower energy, 1s are closer to the nucleus. Oh, I put 4. The 1s electrons are core and 2s are valence, okay? And then, oh, the 4th one, if you thought of this instead, is 2s orbitals have a node and 1s does not, because the node happens in between the 1 and 2s. All right, so next one. Elemental boron reacts with fluorine to form BF3, a gas. Write a balanced chemical equation for the reaction of solid boron with fluorine gas. Oh gosh. Sorry, hang on a second. Ooh. Goodness, that's what I get for trying to make lesson videos when I've literally been teaching every minute of today. Hopefully my throat can make it. It looks like we only have a couple more. So it says, write the balanced chemical equation for the reaction of solid boron. So we have boron. It's not a diatomic, so I'm just going to put B. With fluorine gas. Fluorine is a diatomic, so I need the 2 there for that one. All right, and then it tells me it makes BF3 gas. All right, and I can go back and put the solid and the gases if I want to. I don't need those to balance it though. So I have 1B, 1B, 2F, 3F. So remember the way you fix the 2 and a 3 is making those 6. So 2 times 3 is 6. 3 times 2 is 6. But now I have 2 borons, so I put 2 borons right there. All right. So I think I need this for the next part of this question. So let me click first. Okay, so there's our reaction. All right. So it says delta HF for BF3 gas is negative 1,135.6 kilojoules per mole. Calculate the standard enthalpy change in the reaction of boron with fluorine. All right, so we haven't done delta H of formation in this class yet. I saved chapter 5, which kind of deals with this, to go with chapter 19, which is thermodynamics. But that's okay. We did learn about this in honors, so let's look at this real quick. All right, so we start with our reaction. And so if you look, I have 2 moles of BF3. Okay, I'm getting that from right here. Okay, so if this is the delta H for 1 mole of BF3, then obviously I just need to multiply it by 2. Okay, so I'm starting with 2 moles of BF3, and I know that there is negative 1135.6 kilojoules per 1 mole of BF3. Now you may be wondering, well, how do we know it's per 1 mole? Well, it's because it's per mole. It doesn't say per 2 moles or anything like that. So I just multiply it by 2. And so when I did that, I got negative 2,271.2 kilojoules. So remember how we talked about this is kind of like the mole heat ratio. So it's kind of like stoichiometry and thermochemistry all having a baby together. All right, so let's move on to our last part. So we'll see more of that delta H happening when we get to chapter 5 and thermodynamics together. All right, so the last one says, when BCl3, also a gas at room temperature, comes into contact with water, the 2 react to form hydrochloric acid and boric acid, which is H3BO3, a very weak acid in water. Write a balanced net ionic equation for this reaction. See, this is great because some of y'all have been struggling with net ionic equations. All right, so it says BCl3 is going to come into contact with water and make hydrochloric acid and boric acid. Okay, so I start with my BCl3, which it told me is also a gas. It's going to come into contact with water unless they specify. I'm safe to say that's a liquid. It tells me it forms hydrochloric acid. So remember, if it ends in acid, it starts with H. Hydrochloric means it just comes from chloride, which is Cl, which is going to be positive and negative. And remember, if they don't specify, an acid is aqueous. All right, and then boric acid, which they were nice enough to tell us what that is. A very weak acid in water. So that, of course, is aqueous. All right, so y'all, the important thing to remember is this is a strong acid. That means it's going to split up. This, they told me, is a weak acid. That means it's going to stay together. That's important for when we decide what we're going to not write on either side. All right, so if you look, I don't have anything aqueous on both sides, so I have to keep everything. So a gas. Oh, wait, let's balance it first. So I have B and B. I have 3 Cls, but here I just have 1, so I'll put a 3. I have 2 hydrogens. Here I have 3 and 3 more, which is 6, so I'll put a 3. And then 3 oxygens, 3 oxygens. All right, so now we're ready to write. Sorry about that. So a gas, we don't change at all, so I'm going to keep that together. A liquid, we also don't change at all, so I'm going to keep that together. This is going to split up, so it doesn't matter that neither of them are spectators and they both did something. I still have to split it. So I have 3H positive, and don't forget to distribute that 3, 3Cl negative. And then the weak acid is going to stay together. Because remember, weak acid just means it does not dissociate into ions very much. Alright, so that's why it's important for you to know the difference in your strong acids and weak acids. Okay, I gave you the list of which strong and which weak back in Unit 1. Alright, so hopefully you thought Chapter 6 was pretty easy. Electron configuration is usually one of y'all's strong areas, so hopefully it still is. Otherwise, go back to Chapter 5 for my honors.